Alright, so in this lesson we're going to start looking at the idea of conservation of momentum. So conservation of momentum, I would say in terms of ideas in physics, this is probably one of the big concepts, one of the big key ideas in physics. That if you have a system which is considered to be closed and isolated, the linear momentum of that system is conserved. So what's true of a system that is closed and isolated is that the net external force acting on that system is zero, which means if you add up all the forces that act on that system that come from somewhere outside that system and you get zero, that means the momentum of that system has to remain conserved. What this means is the total momentum of the system at time t1 has to be equal to the total momentum of the system at some other time t2. So let's kind of look at some example problems where this becomes important. A lot of the problems that we look at where conservation of momentum becomes important look like collisions, objects running into one another, objects breaking apart, those types of things. We'll look at other situations later where the idea of conservation of momentum can be used to solve other types of problems dealing with closed systems. So here we have a space hauler and a cargo module with a total mass of m, and it's going to be traveling in a straight line through space at an initial velocity of 2100 kilometers per second relative to the sun. So maybe it's traveling away from the sun at 2100 kilometers per second. So using a small explosive charge, the cargo module, which has a mass of 0.2 m, is launched away from the hauler at a velocity of 500 kilometers per second relative to the hauler. And what I want to know is what is the velocity of the hauler relative to the sun after the cargo module is released. So here we go, we have this thing that's moving this direction. I'm going to make the assumption that the hauler is behind, or the cargo module is behind the hauler, that the hauler lets go of the cargo module. And so here's what's happening after the collision. So what does this mean here, this 500 kilometers per second relative to the hauler? So this means is that there's a relationship between Vm and Vh that looks like this, that Vm plus 500 equals Vh. What this does not mean is that with respect to the sun, the module is moving 500 kilometers per second slower than the than the hauler. So this is what's called relative velocity. We can talk about that a little bit more. It's kind of an interesting concept if you're looking at how objects are moving with respect to one another. So we're going to do momentum initial equals momentum final. And so the initial momentum, m times v initial, has to be equal to 0.2 m, the mass of the module, times the velocity of the module, plus 0.8 m, the mass of the hauler, times the velocity of the module, hauler, vh. So if I divide everything by m, that means the m cancels out. Now I know a relationship between Vm and Vh, that Vm, what I'm ultimately trying to find, is equal to Vh minus 500. So let's plug that in for Vm. At this point we can actually now solve it for Vh. If we substitute that in, 0.2 times Vh minus 100 plus 0.8 Vh equals V initial. Well, V initial equals Vh minus 100. The reason for that is I've added 0.2 and 0.8. So V initial plus 100 equals the speed of the hauler. So that means the hauler is now moving 2200 kilometers per second with respect to the sun. So that would be how to kind of work out a problem of this nature. Now there are some special types of collisions that we come across in physics when two objects collide with one another. And here are kind of four definitions you'll sometimes see with collisions. You'll sometimes see elastic, which means that both momentum and kinetic energy is conserved within a system. That means if you take the momentum before a collision and kinetic energy before the collision, they're the same numbers after the collision. Inelastic means momentum is conserved but kinetic energy is lost. Completely inelastic would tell you that objects stick together after the collision. That's as much kinetic energy being lost as possible. And sometimes you'll see what's called superelastic. These are ones where kinetic energy is actually gained in the collision. You might ask, well, how does that happen? Well, it could happen if you have something like, let's say, a spring within the collision, and somehow the spring is causing there to be more energy after the collision than before the collision. Maybe you have a spring that's tightened up, and when the two objects run into one another, the spring expands. That would be a good example of a superelastic collision. So let's look at an elastic collision and say we want to find the final velocity of both if I know m1, m2, v initial 1, and v initial 2. So what I'd do is I would start with these two equations. Here's conservation of momentum. There's conservation of kinetic energy. And then a bunch of algebra is going to happen to solve for v final 1 and v final 2. It's worth pointing out that I have a system of two equations with two unknowns. It can be possible to solve just those two equations. I'll say I can post a derivation if you're really interested in knowing that derivation. It takes somewhere between about 15 and 25 minutes to actually go through that derivation. What you end up with is these two equations. How do velocity 1 and velocity 2 relate to one another? Or how do final velocity of 1 and final velocity of 2 relate to one another? And so you end up with two equations that look like this as your two final equations. So they're pretty complex if you actually look at them. You can actually check to make sure that this is true. If you want to check to make sure that it's true, plug them into either v final 1, v final 2, or v final 1 squared, v final 2 squared, and work them out, and you'll see that this actually works out that way. So the second one is my completely inelastic collision. This one is actually easier to derive because v final is the same. So if v final is the same, we can solve for v final by combining like terms on the right hand side and dividing it out. The v final is related to the initial momentums of both of the two systems added together divided by the mass of the entire system. So let's look at a collision problem. Here I have the collision of two carts is done in a lab, and the data is collected from the lab, and the graph is shown to the right. Cart 1 has a mass of 0.5 kilograms, cart 2 has a mass of 1 kilogram, and what I want to know is the collision elastic? Now some of you may be familiar with this particular diagram, depending upon when you took physics and what version of the momentum exam you got. You maybe or maybe not saw this diagram. This is one that I've used before on exams in my regular physics class. So if we look at this diagram, here's what's happening before the collision, here's where the collision's happening, and this is what happens after the collision. So the first thing I need to do is figure out initial velocity and final velocity. It looks like the initial velocity of cart 1 is 3 meters per second. Cart 2 is initially at rest. Looks like the final velocity of cart 2 is 2 meters per second. And the final velocity of cart 1 is negative 1 meters per second. Now that negative 1 is important because remember, momentum is a vector. So my first question would be, is momentum conserved? If momentum is not conserved, this isn't a collision that happens in the real world. Or at least not one where the net external force is 0. There must be something else happening. So P initial equals P final. So M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So if I plug in all my values, what I get is 1.5 kilogram meters per second is the momentum before, 1.5 kilogram meters per second is the momentum after. Momentum is conserved. So we at least know that this is a collision that happens normally in our everyday lives. Second question to answer, is it elastic? Is kinetic energy conserved? So 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared, does that equal 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared? So I plug my numbers in. We find is there's 2.25 joules of kinetic energy both before and after the collision. Sure, kinetic energy is conserved, and guess what? This is elastic. So in the next lesson, we're going to start looking at what happens if collisions are in two directions, and maybe think about what happens if they're in three directions. What we've looked at with our collisions so far are things that only move in one dimension.